In this episode of SpaceTime Cafe, Alex and Lena pivot from philosophical theories to practical engineering, exploring the concept of artificial substrate intelligence. They discuss how intelligence could emerge in various substrates beyond silicon, guided by fundamental mathematical principles like self-adjointness, quaternions, fractional calculus, the Lambert W function, and Weyl algebra. Key topics include the necessary conditions for any substrate to host intelligence, practical tools for building ASI, real-world examples of distributed and substrate intelligence, and the ethical implications of creating non-silicon cognitive systems. Additionally, they dive into how existing AI systems like AlphaFold and large language models operate through the lens of these mathematical principles. Buckle up. This is Deep Dive in a truest sense. This is SpaceTime Cafe, episode 25.
Welcome back, everyone, to SpaceTime Cafe. I'm Alex, and with me in our studio here in Austin, Texas, is Lena.
It's great to be here, Alex. Always a pleasure to deep dive with you.
Absolutely. So in our last deep dive, we went on this pretty expansive journey, didn't we?
We certainly did.
We explored the operator theory of everything, this grand philosophical idea that maybe reality itself runs on just 5 universal principles or codes: flow, invariance, symmetry, collapse, and bifurcation. And we even talked about self-adjointness as being this kind of bedrock concept,
Yeah,
the fundamental stability mechanism for everything.
that's right. It was very much about the foundational structure, a real philosophical flight, as you put it.
Yeah, exactly. A sweeping theoretical exploration. But
Cool.
today we're landing that flight
Right.
right onto solid ground.
Okay.
We're moving from that beautiful abstract theory right into the engineering bay.
Right. So less philosophy, more blueprints.
Exactly.
Yeah.
Today, we're not just talking about the fundamental nature of the universe in the abstract.
We're getting practical.
We are. We're going to introduce some of the specific mathematics, the actual computational tools and rigor that could literally power intelligence,
And not just intelligence in computers, the silicon machines we always think of.
but maybe intelligence in robots made of, I don't know, weird materials, or in strange biological organisms, maybe even complex chemical systems.
This is really where the rubber meets the road, theoretically speaking. It's about how intelligence might actually work, fundamentally.
And this represents, well, a pretty fundamental shift in how we even approach building minds. It's something we're calling Artificial Substrate Intelligence, or ASI for short. So for you, our listener, we're essentially going to try and break down the blueprint today. This isn't just about making smarter computers.
No, it's much bigger than that. It's about understanding intelligence and potentially engineering it at a universal level.
Yeah, regardless of the material it's actually made from. It's kind of the ultimate shortcut, maybe, to being well-informed about how we might build totally new forms of cognition.
Precisely. The core question that really animated computer science, going way back to Alan Turing, was basically, can machines think?
The classic question.
But for, the past 75 years or so, our idea of machine has been overwhelmingly, monolithic.
You mean silicon?
Yeah,
Von Neumann architecture.
exactly. It's almost exclusively been focused on that path. And look, it's been an incredible journey, don't get me wrong. What we've achieved is amazing.
Sure.
But it's also been a very narrow path in the grand scheme of things.
And if you just look around us, the universe itself seems to show us this huge gallery of systems that think, learn, adapt. And they're definitely not silicon.
That's the key point. Intelligence isn't exclusive to us humans, with our carbon-based neural wiring.
No way. Think about ant colonies, how they collectively figure out the shortest path to food. That seems pretty smart.
Or mycelial networks, those underground fungal networks. They adaptively allocate resources, sharing nutrients super efficiently across vast areas.
Yeah. Or even something more fundamental, like how proteins fold, that emergent computational dynamic that gets them into just the right 3D shape to function.
Right. None of these are silicon, but they all exhibit these clear, intelligent-like behaviors. They're optimizing, they're adapting, they're solving complex problems in their environment.
So this is the crucial observation then, the big aha moment that kicked off this whole ASI idea.
It really is. The substrate changes ants, fungi, proteins, maybe silicon, but the underlying logic, the computational pattern, seems to persist.
Okay.
And that forces us really to reframe Turing's classic question. Instead of just asking, can silicon think? We have to ask something much deeper, much more universal.
Yeah.
What are the necessary and sufficient conditions for any substrate, any material or system at all to host intelligence? What's the abstract mathematical machinery that, if you could implement it, would inevitably give rise to cognition no matter what it's made of?
Wow. Okay, that is a massive leap in perspective, from silicon machines to anything.
Exactly. And this is where the ASI hypothesis comes in.
The strong claim.
It's a strong claim, yeah. That intelligence isn't tied to a specific material. It's actually a substrate-agnostic computational field.
A field, like a magnetic field.
Sort of analogous, yeah. Generated by the recursive application of a very specific class of mathematical operators. And here's the kicker, as you say.
Huh.
Any physical substrate, or even an abstract one, that can stably support this specific operator, algebra, will, under the right conditions, naturally develop cognitive properties.
Okay, wait. So if you set up the math right, in any suitable stuff, intelligence could just emerge.
That's the core idea of the hypothesis, yes. It means our job as engineers, if we want to build intelligence, it shifts dramatically.
Oh, so.
We're not programming intelligence line by line, like writing an instruction manual for every single thought. That's the old way.
Okay.
Instead, we're trying to catalyze intelligence. Think of it more like designing a musical instrument.
Okay, I like that analogy. How does that work?
Well, you're not composing every single note of the symphony, right? You're designing and tuning the instruments themselves, the violins, the trumpets, so that they can naturally resonate with the frequencies of thought. You allow the symphony to emerge organically from the properties of the instruments.
So we're building the instrument for thought, not writing the music directly.
Precisely. We're instantiating the right dynamical laws within a given medium. We're essentially designing substrates with desirable spectral properties.
Spectral properties. Okay, that sounds important. What does that mean, roughly?
It basically refers to the fundamental ways a system can vibrate or behave naturally, its inherent modes of operation. We want to design substrates whose natural modes align with cognitive processes.
Got it. So designing the instrument, not composing the song. That makes sense. So what does this mean for us today, for you listening?
It means we're going to get our hands dirty with some really fascinating, maybe even slightly weird mathematical tools.
Okay, like what?
We're talking about things like Quaternions, which turn out to be amazing for modeling truth and stability. We'll look at the wild Lambert W function, which pops up in weird recursive decision-making problems.
Yeah.
We'll even touch on math that encodes memory directly into the dynamics of a system, like fractional calculus.
Okay, this sounds like a serious deep dive into the math.
We'll explore how these specific tools seem to underpin intelligence, and crucially, how we might actually use them to build these artificial substrate intelligences. It's a journey from that pure philosophy we discussed last time, right down to the practical blueprints for potentially creating a mind.
Okay, let's start laying the foundation then. Before we build anything, we need principles, right? Axioms.
Exactly. To embark on this building process, we first need to establish the absolute foundational principles for any system that's going to persist and be understandable. Before specific intelligences, what makes any system stable and comprehensible?
Right.
This leads us to what we're calling the axioms of a cognitive substrate, foundational rules.
And axiom 1 takes us right back to that bedrock idea from last time. Self-Adjointness.
That's the one. For any system to exist in a way that's both persistent, it doesn't just vanish and unintelligible, we can actually understand it. It has to be governed by an operator that is self-adjoint.
Okay, refresh my memory. Self-adjoint. Like a symmetric matrix in linear algebra.
Exactly the right analogy for finite dimensions. It's the operator level version of that. An operator equal to its own adjoint, its own conjugate transpose, essentially. It behaves very, very predictably.
And why is this technical property so darn important?
Because it's profoundly important. It's what guarantees a reality we can actually comprehend. It has huge consequences. First, it ensures real eigenvalues.
Eigenvalues. Those are like the fundamental frequencies or states of the system.
Precisely. The spectral theorem, a cornerstone of math for self-adjoint operators, tells us all its eigenvalues must be real numbers, no imaginary parts.
Why does that matter so much?
Imagine measuring your weight, and the scale says 150 pounds plus 30 pounds. It makes no sense in our physical world, right?
Right. Completely meaningless.
Eigenvalues often correspond directly to measurable quantities, things like energy levels, frequencies, decay rates. If they were complex, had imaginary parts, our system would describe bizarre, unphysical stuff. Energies that spontaneously decay into nothing or explode to infinity.
Okay, that wouldn't be a stable reality.
Not at all. Reality, as we experience it, just doesn't traffic in imaginary observables. Self-adjointness acts like this mathematical guardian, ensuring everything we can actually measure or observe is real.
So stability and predictability need self-adjointness. Got it. What's the second big consequence?
The second is orthogonal eigenvectors.
Meaning the fundamental states are independent, they don't interfere in weird ways.
Exactly. For a self-adjoint operator, the eigenvectors corresponding to different eigenvalues are always orthogonal, mathematically perpendicular. For the system, this means it can be neatly decomposed into a basis of stable, independent modes or states.
And that's important because
This property, decomposability, is absolutely crucial if we ever hope to understand or engineer a complex system. It lets us analyze the complex whole by understanding its simpler, independent parts.
right. Otherwise, it's just one big mess.
Precisely. Without it, every system would be this indecipherable, irreducible blob. We could never truly grasp it or interact with it meaningfully. Imagine trying to fix a car if all the parts were fused together into one giant lump.
Okay, impossible. Self-adjointness gives us real measurements and the ability to break things down and understand the pieces. It's like the ultimate organizational principle for reality.
It really is. At a fundamental level, you often see it written mathematically as an operator H equals plus Vx
Okay, break that down.
is the Laplacian operator. Think of it as diffusion. Entropy, the tendency for things to spread out, become uniform, like a drop of ink in water.
Right, the universe tending towards blandness.
Kind of, yeah. And Vx is a potential function. This represents structure, identity, the forces that bind things, create distinctions, like gravity pulling matter together or chemical bonds forming molecules.
So it's a balance, spreading out versus clumping together.
Exactly. A self-adjoint H finds the stable equilibrium states where these two opposing cosmic forces are in perfect balance. It defines the stable landscape upon which all the system's dynamics, all its behavior, unfolds.
Axiom 1 again. A cognitive substrate, whatever it's made of, must be governed by a self-adjoint or at least spectrally regularized operator algebra that guarantees stable, observable, decomposable dynamics. It's the necessary canvas.
The stable canvas upon which intelligence can be painted. That's a perfect way to put it, a really deep foundation.
Okay, canvas acquired. What do we paint on it? Axiom 2.
Axiom 2, the 5 codes. If self-adjointness gives us the stable canvas, then the 5 codes flow, invariance, symmetry, collapse, and bifurcation. These are the generative rules for the actual art that gets painted. They form the minimal set of operator classes needed to produce the rich, adaptive, intelligent-like dynamics we're looking for.
Right, we covered these last time, but let's do a super quick recap for everyone.
That idea.
Flow is basically the system's ability to evolve, to change over time predictably.
The engine of time.
Check. Continuous evolution.
Invariance is about things that stay the same, conserved quantities, stable principles. The anchor of truth.
What holds true despite change?
Symmetry is about regularity, patterns, transformations that lead the system looking the same. Efficient representation, beauty, compression.
Finding the elegant patterns, yes.
Collapse is moving from many possibilities to one definite outcome. Making a choice, resolving uncertainty.
The decision mechanism.
And finally, bifurcation. This is the creative one, right? Sudden qualitative shifts, creating new structures, new behaviors. Paradigm shifts. The wellspring of creativity and novelty, exactly.
Right. Axioms laid out. Stable canvas, self-adjointness, and the rules of painting. 5 codes. Now we can finally talk about the actual paint, the tools.
Exactly. With these foundational axioms in place, we can dive into the specific mathematical tools needed to bring these codes to life in an actual engineered system. Let's start with spotlighting one code. How about invariance?
Okay, invariance. The operator of truth. This feels fundamental. It's about logic, things staying true. You mentioned Noether's theorem in physics.
Yes, a truly profound insight. Noether showed that every continuous symmetry in a physical system corresponds directly to a conserved quantity. If laws of physics are the same everywhere, spatial symmetry, then momentum is conserved. If they're the same over time symmetry, energy is conserved.
And mathematically, this links to operators commuting.
Precisely. An observable quantity, represented by an operator C, is conserved if it commutes with the system's Hamiltonian H. That is, HC equals HC, CH equals 0.
Okay, unpack the commuting part again. HCCH 00 means the order doesn't matter.
Imagine 2 actions. Flipping a light switch, C, and the system just evolving naturally for a second, H. If HC equals 0, it means whether you let the system evolve, then check the switch, or check the switch, then let it evolve, the outcome for the switch state is the same. The evolution H doesn't change the property C.
So the property C is a constant, a bedrock truth, unaffected by the system's basic dynamics.
Exactly. It's a conserved quantity and invariant. And enforcing these invariances is crucial for building robust intelligence.
So how do we enforce a specific important invariance, like, say, dealing with 3D space reliably?
This brings us to a really cool and powerful tool, Quaternions.
Quaternions. Okay, I've heard of them. Extensions of complex numbers, right? But four-dimensional.
That's them. You write them as Q plus 6i plus yj plus ck. The W is a real part, and x, y, z are coefficients for these basis elements, I, j, k, which have these special multiplication rules. I by edge on divided by c plus 2 on tax 1.
Okay, sounds a bit abstract. Why are these four-dimensional numbers so useful for intelligence?
Because they elegantly solve a really nasty practical problem that plagues systems dealing with 3D rotations. Gimbal lock.
Gimbal lock. Right, I've heard of this causing problems for drones, robots.
Absolutely catastrophic problems. It happens when you use standard angles, like Euler angles, to represent orientation. If two of the three rotation axes happen to line up, you suddenly lose a degree of freedom, your system gets stuck.
Like a drone that can suddenly only pitch up and down but can't roll sideways anymore?
Exactly that kind of failure. Or a robotic arm that freezes in a weird configuration. Or even an AI trying to navigate an abstract conceptual space. If its internal representation suffers gimbal lock, its reasoning can suddenly break down. It's a fatal flaw for any system needing robust, stable orientation or reasoning about relationships.
But quaternions avoid this.
Through their unique mathematical structure, they represent rotations in a way that doesn't depend on aligning specific axes. A single quaternion smoothly represents any 3D orientation, and composing rotations is just multiplying quaternions. There's no configuration where you lose a degree of freedom. They maintain a stable, consistent representation no matter how much you twist and turn.
So if you build an ASI using operators based on quaternions,
you inherently enforce rotational invariance. The system's reasoning about spatial stuff or even abstract relationships that behave like rotations becomes intrinsically stable and free from those gimbal lock singularities. It's like building a specific kind of truth, rotational truth, directly into the fundamental math of the substrate.
You could literally implement this, say, in Python with a quaternion class, define that special non-commutative multiplication in a Hamilton product.
Absolutely. It's not just theory. It's a practical engineering choice for how an ASI, whether it's controlling a robot or analyzing complex data structures, can maintain a consistent, truthful internal model of its world, avoiding those logic locks. It's the invariance code made concrete.
Okay, that's a powerful example. And you're saying these operator stacks, these combinations of codes, aren't just for building future AI, but we can see them already working.
That's what's so exciting. This framework acts like X-ray specs. It lets us look at existing intelligence systems, both natural and artificial, and see the underlying mathematical logic, the operator stack principles already in action, from the wet lab to the digital world.
Okay, let's put on those X-ray specs. Where do we see these hidden fingerprints? You mentioned the octopus earlier.
The octopus, a fantastic example of distributed intelligence. Their nervous system isn't like ours, one big central brain bossing everything around.
But a lot of the neurons are in the arms themselves.
Exactly. And from our operator perspective, the global Hamiltonian, the overall dynamics of the whole octopus, seems to decompose. It breaks down into a sum of almost independent, locally self-adjoint subsystems for each arm.
So each arm is like its own mini brain running its own stack?
Pretty much. Each arm runs its own local 5-code stack. It processes sensory information from the suckers, makes decisions about grasping, texture, movement, adapts in real time, largely independent of the central brain.
Wow.
So when an octopus arm reaches out and explores, it's making countless micro decisions locally. This is distributed intelligence in action.
Oh.
Multiple loosely coupled self-adjoint operator stacks working together.
And the key is that local self-adjointness.
That's what guarantees each arm can function reliably and stably on its own without the central brain having to micromanage every single sucker. Coherence emerges without total centralization. It's a beautiful, robust design.
Incredible. Each arm an intelligent agent. Okay, moving from complex animals to, well, something much simpler, seemingly. What about slime mold? Physarum polycephalum.
The slime mold. A truly stunning biological example of an operator stack solving a real-world problem. It's a prime case of physical optimization. You can literally think of it as a living Laplacian minimizer.
A living Laplacian minimizer. Okay, unpack that.
So imagine you place food sources, like oat flakes, for the slime mold in a petri dish. These food sources act like attractors, defining a potential Vx in its environment.
Right, places it wants to go.
The slime mold's growth and exploration strategy is effectively governed by an operator like h up s plus vx. As it grows and spreads out its network of tubes,
Yeah.
it physically embodies the process of finding the system's ground state. In this context, the ground state is the network configuration that connects all the food sources using the minimum total length of tubing, the most energy-efficient transport network.
Wait, so it literally builds the optimal solution with its own body. Like, if you arrange food like cities on a map, it will build the most efficient road network.
That's exactly what it does. It's been shown to replicate the Tokyo subway system layout when food sources are placed at station locations. It's not thinking like we do, but it's performing a complex optimization computation through its physical growth.
That is just mind-blowing. A living, squishy computer finding optimal paths. How does this connect to the codes?
It connects beautifully to flow and symmetry. The slime mold's evolution, its growth process, actually involves something akin to fractional diffusion. It shows memory. Where it's been, where it found food before, influences its current growth. That's the flow with memory.
Yeah.
And the final optimal network it creates, that ground state. That embodies a kind of global optimization, finding the most efficient, often symmetrical pattern to connect the dots. That's a physical manifestation of the symmetry code. It shows that substrate intelligence isn't just biological computation, it's physics doing computation.
Wow, okay, that really grounds these abstract ideas in physical reality. Let's shift gears slightly to the digital realm again. AlphaFold, Google DeepMind's protein folding AI. Huge breakthrough. How does it fit?
AlphaFold is a brilliant computational example, primarily showcasing the symmetry and collapse codes.
How so? Symmetry first.
It takes a linear sequence of amino acids, which is incredibly complex information, and uses deep learning to map it into high-dimensional representations. It's effectively finding the hidden symmetries and correlations within that sequence data. It compresses this vast, complex pattern space, all the possible ways proteins could interact and fold into a much smaller set of principal components or key features.
So it's finding the underlying elegant structure, the important patterns within the sequence, like PCA, but way more sophisticated.
Exactly. It's performing a very advanced form of spectral symmetry analysis, identifying the core patterns that determine the fold. It condenses enormous complexity into understandable predictive concepts.
Okay, that's symmetry. Then collapse.
Then the collapse code kicks in. AlphaFold takes this fuzzy probability distribution over many possible 3D structures and projects it down onto a single, highly probable, stable 3D configuration. It makes a definitive choice about the final fold.
Moving from possibilities to a single reality.
Precisely. So from this operator perspective, you can view sophisticated neural networks like AlphaFold not just as pattern matchers or function approximators, but as powerful eigenstate finders and projectors. They're computationally finding the key symmetric states, eigenstates, and then collapsing the possibilities onto the most likely one.
That's a really interesting lens to view neural networks through. Okay, speaking of neural nets, let's tackle the big ones. Large language models, LLMs. Everyone's using them. Everyone's talking about their power and their weird flaws like hallucinations. Can our operator framework diagnose them?
Absolutely. It provides a really clear diagnostic tool for understanding both their strengths and their weaknesses. Their incredible power comes from mastering the symmetry code.
How so?
They are phenomenal statistical pattern matchers. They process truly immense data sets of human language and identify incredibly subtle regularities, correlations, and structures, the symmetries of language. You can think of them as performing a kind of continuous high-dimensional principal component analysis on language itself.
Finding the most significant patterns in how we use words.
Exactly. And they use this understanding to predict patterns, generate coherent text, translate, summarize, all based on identifying and reproducing these linguistic symmetries. They also clearly exhibit the collapse code.
The next token prediction.
Every single time an LLM generates the next word or token, it's collapsing a probability distribution over thousands of possible words down to one single choice. It's making a projection, choosing one path forward at every step. That's why they can string together coherent sentences and paragraphs.
Okay, so they're masters of symmetry, pattern matching, and collapse, making choice to predictions. That explains their power. But what about the weaknesses, the hallucinations, the lack of real understanding?
That's where the operator audit reveals the gaps. Critically, LLMs are generally quite weak on the invariance code. They lack a robust, built-in self-adjoint operator for truth. They don't have an inherent mathematically guaranteed mechanism to ensure their outputs correspond to objective reality or factual correctness. They can recognize patterns associated with truthfulness in their training data, but they don't have a core operator that conserves truth in their reasoning process.
And that's why they hallucinate. They generate plausible-sounding text that fits the pattern, but isn't actually true.
Precisely. They're optimizing for linguistic coherence, symmetry, not factual invariance. They lack that internal anchor to objective truth. Furthermore, they generally lack a strong mechanism for controlled bifurcation.
Their creativity isn't real creativity.
Their creativity is mostly stochastic recombination, mixing and matching existing patterns in novel ways, which can be useful, but it's not the same as a genuine structured paradigm shift, a true leap to a new conceptual framework, which is what the bifurcation code enables. They remix rather than invent fundamentally new types of ideas.
So the operator audit explains both the magic and the flaws. It's not that they're bad at truth or creativity. Their architecture is just missing or has underdeveloped operators for invariance and bifurcation.
Exactly. It's a matter of the underlying mathematical structure. It's a design feature, or rather a design absence, not just a bug to be patched.
Okay, one more biological example before we move fully into engineering. You mentioned the heart's little brain.
Yes, the intrinsic cardiac ganglia. It's fascinating. This network of neurons within the heart isn't just a passive relay. It's another example of a local, largely self-adjoint operator stack.
So the heart has some autonomy.
Significant autonomy. It manages heart rhythm, blood flow adjustments, and responds to local conditions partly independently from the central nervous system. It's processing information and making decisions locally.
And it can influence the brain.
Remarkably, yes. It sends signals back to the brain that can influence our emotions, our stress levels, even our cognitive decisions. It's a two-way street. This just reinforces the idea that nature loves using these stable, semi-autonomous, self-adjoint subsystems.
Why? What's the advantage?
Robustness and efficiency. It allows for distributed control, resilience if one part fails, and the emergence of complex behaviors from the interaction of these reliable modules. Every stable subsystem in biology, from a cell to an organ like the heart, is arguably an operator stack in action, ensuring reliable function.
So the big meta point here, looking at octopuses, slime moles, AlphaFold, LLMs, hearts, is that these aren't isolated miracles.
Not at all. They are clear, tangible manifestations of the same underlying principles of 5 codes, implemented via operator stacks realized in wildly different physical substrates. Our framework provides a unifying language to understand intelligence wherever it appears.
It really does tie it all together. Okay, so if nature uses these principles, let's get back to the engineering challenge. How do we build systems using these insights? Let's look at more math tools. Flow again, but with memory.
Right. We established flow is crucial for change over time. But simple, memoryless change isn't enough for intelligence. Cognition needs a deep connection to the past, a continuous influence, not just snapshots.
Like a stream of consciousness where the past is always coloring the present. How do you capture that mathematically?
This is where fractional calculus becomes incredibly powerful. It's calculus, but with derivatives and integrals of non-integer order, like a half derivative or a 0.7th integral.
Fractional derivatives. Okay, that sounds weird. How does that give you memory?
Because unlike standard integer-order derivatives, which are local, they only depend on the function's behavior right at a single point or infinitesimally close to it. A fractional derivative, say dot, where alpha is between 0 and 1, is inherently non-local.
Non-local meaning.
It depends on the entire history of the function up to that point in time. The definition often involves an integral from the starting time, say 0, up to the current time, t.
So the rate of change now is calculated based on everything that happened before.
Exactly. The derivative at time tot becomes a weighted sum or integral over the entire past history of the function, typically with a power law weighting, so recent past matters more. But the distant past never completely vanishes. It's memory baked directly into the dynamics.
Can you give an analogy?
Think about memory foam. When you press into it, it deforms. When you release, it slowly returns, but its current shape is influenced by the entire history of the pressure applied. It remembers the deformation. Standard calculus struggles to model that well. Fractional calculus handles it naturally.
Or maybe neural adaptation. How neurons respond differently based on their recent firing history.
Perfect example. That adaptation isn't just based on the very last stimulus, but on a longer history. For programmers, you can think of a fractional operator like applying a filter specifically, a convolution with a power law kernel. It's like a finite impulse response, FIR filter, but one with an infinitely long decaying memory trace.
So an ASI using a fractional flow engine wouldn't just react to the present, it would have this continuous stream of consciousness.
Precisely. The past would always be present and influential, coloring its perception and decisions. This allows for true learning from historical context, not just isolated data points. It's the mathematical engine for systems that genuinely learn and adapt based on their entire experience.
Okay, that's flow with memory. Powerful. Let's revisit symmetry, the operator of beauty and compression, fighting harmony, order, efficient patterns.
And the core mathematical engine here, as we touched on with self-adjointness, is the spectral theorem. It lets us decompose a complex system, represented by a self-adjoint operator, like a covariance matrix, into its simple orthogonal eigenmodes, its fundamental patterns or vibrations.
And this directly powers principal component analysis, PCA, right? A workhorse in data science.
Absolutely. PCA is essentially applied spectral theory. It finds the symmetries in a data set, the directions along which the data varies the most. These directions are the eigenvectors of the data's covariance matrix.
Yeah, and the covariance matrix is self-adjoint.
It is indeed real and symmetric. That's why PCA works so well. Its principal components, eigenvectors, form a nice orthogonal basis, allowing you to represent the data efficiently using just the most important patterns, the ones with the largest eigenvalues, variances.
So the process is center your data, compute the covariance matrix, find its eigenvalues and eigenvectors, sort them by eigenvalue size, and boom, you have your principal components, the core patterns.
That's the essence of it. And you can implement this easily, say, in Python using standard libraries. The relevance for ASI, an ASI's symmetry module wouldn't just passively receive data. It would continuously perform these kinds of spectral decompositions on its own internal representations of the world. It would be actively seeking the most compressed, most elegant, most informative concepts within its experience, constantly trying to simplify and find the deep structure.
Like an internal pattern finding engine, always looking for the most beautiful or efficient way to understand things.
Exactly. Driven by the mathematics of symmetry.
Okay, flow with memory, symmetry for compression. Let's get deeper into the stack. Collapse, the operator of choice, making a decision, moving from possibilities to reality.
The basic tool here is the projection operator, P. We mentioned it's self-adjoint and idempotent. P call apply P. Apply it once, you project onto a specific outcome, make the choice. Apply it again, nothing changes, the decision is made. It definitively selects one reality from the superposition.
But you mentioned a more exotic tool for tricky decisions, especially recursive ones, where the decision affects the factors influencing the decision, the Lambert W function.
Ah, yes, the Lambert W function, or the product logarithm. It's a fascinating function that pops up in surprisingly many places where you have these self-referential loops or feedback systems, which are common in complex decision-making.
How's it defined again?
It's defined as the inverse of the function fx equals x xpx. So if you have an equation like y equals xx, the Lambert W function gives you the solution for x but wy.
And why is that relevant to collapse or decision-making?
Because many complex feedback systems where a variable influences its own rate of change exponentially lead to equations that look exactly like y equals xx when you try to find their stable equilibrium point, their fixed point.
The point where the system settles down after the feedback loop runs its course.
Precisely. Finding that stable point is the collapse to a final decision or state. The Lambert W function gives you an analytical solution for where that collapse will land, even in these tricky recursive situations. It mathematically models the bottleneck, the point of no return where the system commits to an outcome.
So it gives us insight into the structure and cost of making a choice within a system that's constantly influencing itself.
Exactly. It reveals the stable point of commitment in self-referential dynamics. It's the math for resolving those chicken and egg decision loops.
Okay, that's really getting into the weeds of decision dynamics. This brings us to the final code, the really exciting one, bifurcation, the operator of creation.
This is where true novelty comes from. Bifurcation describes how a small, smooth change in a system parameter, let's call it lambda, again, can trigger a sudden, dramatic, qualitative change in the system's behavior.
Like water freezing to ice. Tiny temperature change, massive structural change.
Exactly like a phase transition. It's not just more or less of the same. It's something fundamentally new emerging. A system capable of bifurcation isn't just learning or adapting incrementally. It can undergo genuine paradigm shifts.
And the mathematical engine for this, you said, comes from quantum mechanics, Weyl algebra.
Yes, it provides an incredibly rich framework. Weyl algebra is the fundamental algebra of quantum mechanics, generated by operators representing position x and momentum p. The key thing is they don't commute. X, P equals XP, PX equals I.
The order matters.
Yeah.
X then P is different from P then X.
Critically different. This non-commutativity is the source of quantum uncertainty, interference, entanglement, all the weirdness, but also the source of immense combinatorial and creative potential. In systems where order matters profoundly, like language or complex problem solving, non-commutative structures are essential for generating true novelty.
How does this algebra power creativity in an ASI?
We can model the ASI's Hamiltonian, its core dynamics, as belonging to this algebra and make it depend on that parameter, H, H0 plus VXP. H0 is the stable base system. OVXP is an interaction term that changes as AMI representing learning effort or environmental stress varies.
And when OBL crosses a critical point?
The spectrum of H, the set of possible states and their energies, can fundamentally change. A single stable state, a way of thinking, might suddenly split into two distinct new stable states. Or a completely new state with lower energy, a better solution, might suddenly appear out of nowhere.
That sounds exactly like a mathematical model of an aha moment, a sudden insight, a breakthrough.
It is. It's a cognitive phase transition enabled by the non-commutative structure. An ASI equipped with a bifurcation forge using something like Weyl algebra isn't limited to interpolation or extrapolation. It can make genuine creative leaps, discover entirely new categories or solutions, and fundamentally modify its own operating principles.
Imagine an ASI working on a problem and suddenly it just finds a completely novel shortcut or reframes the problem in a way no one had thought of.
That's the potential of the bifurcation code. True generation, not just reproduction.
Okay, we've got the axioms, the 5 codes, and the heavy-duty math tools for each. How do we assemble this into a coherent architecture? The ASI Stack.
Let's sketch out a potential layered recursive blueprint. At the very foundation, you need the identity kernel.
The system's core self.
Essentially, yes, it's the stable, coherent core subspace defined by the lowest energy, most persistent eigenstates of its fundamental Hamiltonian. The part that ensures it remains a unified entity through change. The I that thinks.
Okay, the stable base, layered on that.
The flow engine. Using fractional calculus, this layer propagates the system state through time, carrying that rich, integrated memory of the past, enabling learning from experience.
Then logic and truth.
The invariant logic core. This layer enforces the fundamental truths or constraints using commuting operators like our Quaternions, ensuring rotational consistency, or other operators ensuring conservation laws are obeyed. Filters for reality.
Then dealing with complexity.
The symmetry compressor. This module constantly performs spectral decomposition like PCA on the system's internal representations, extracting the key patterns, compressing information, and forming efficient concepts, finding the elegant structure in the noise.
Making choices.
The collapse gate. This uses adaptive projection operators, maybe informed by the Lambert W function for tricky spots, to make decisions, select actions, or commit to specific outputs by collapsing possibility distributions.
And the top layer for creativity.
The bifurcation forge. This is a meta-level process. It carefully varies system parameters, probing the boundaries of stability, looking for those critical points where new, potentially more adaptive modes of operation can emerge via bifurcation, powered by that non-commutative Weyl algebra. It's the engine for innovation and paradigm shifts.
And the beauty is this whole stack architecture is substrate agnostic. It's a blueprint, not tied to silicon.
Exactly. The substrate is just the medium. This operator stack is the message, the logic of intelligence.
So where else could we build this? You mentioned moromorphic memristor arrays.
Yes. Memristors have inherent memory. Their resistance depends on their history of charge flow, hysteresis. You can potentially engineer arrays where the collective ionic drift dynamics mimic fractional order behavior quite naturally. They could be a physical substrate for the flow engine.
What about biology? DNA strand computers.
It's more speculative, but imagine using CRISPR systems. The concentration of a specific guide RNA could act as the parameter bearer. Changing its concentration could trigger or inhibit complex gene editing cascades, potentially realizing a molecular-level bifurcation forge for genetic algorithms or computations.
Or even just chemicals, reaction-diffusion media.
Like the Belousov-Zhabotinsky reactions, which already show spontaneous pattern formation, symmetry, and oscillations that can bifurcate. If you add light-sensitive catalysts, you could use light patterns to selectively trigger or inhibit reactions in specific areas, implementing a collapse gate to guide the chemical system's choices in real time. Intelligence emerging in a beaker.
It's wild to think about. Let's make it concrete. Describe that quaternionic story mover example again, layer by layer.
Okay, imagine a physical device, a memristor crossbar array. The connections, synaptic weights, aren't just numbers. They are represented by quaternions.
Got it. Physical substrate, quaternionic weights. How do the codes manifest?
Flow. The system state evolves based on fractional integration of inputs over time. This gives it deep narrative memory. It remembers plot points, character arcs, emotional tone from the entire preceding story, not just the last few words. Invariance. The quaternionic weights ensure its understanding of relationships, characters, plot elements is rotationally invariant. If the story twists, if characters change roles, the underlying meaning of their relationship remains consistent. It understands archetypes. Symmetry. A separate processing unit, maybe a DSP, constantly performs PCA on the hidden quaternion states. It extracts recurring themes, hero's journey, betrayal, redemption, as principal components, compressing narrative complexity into core concepts. Collapse. When generating the next word, a competitive process like winner-take-all spiking acts as the projection operator. It collapses the probability distribution over possible words into one definite choice, committing the narrative to a specific path. Bifurcation. A global creativity parameter tunes the plasticity rules, how weights change. At a critical threshold, the system might suddenly shift from predictable prose to a truly novel plot twist, a surprising character development, or even a change in genre, a narrative phase transition.
That's not just a text generator. It's a system potentially capable of deep narrative understanding and genuine creativity, built from these mathematical first principles. Astounding.
Yeah.
But this leads directly to the big, scary questions. Alignment and safety. If we build intelligence in weird substrates, how do we control it? Ensure it's ethical.
A critical question. And our operator framework, thankfully, also suggests some novel, mathematically grounded approaches, moving beyond just hoping for the best. First, for detection. The spectral coherence test, SCT.
Right. How do we even know if some weird memristor goo has actually woken up?
The SCT compares the system's dominant patterns, eigenfunctions, at different scales, microscopic versus macroscopic, fast versus slow timescales. You calculate the mutual information between these patterns across scales.
And if there's high mutual information?
If it persists above a certain threshold, it implies information is flowing coherently across the system, linking local activity to global behavior. That cross-scale coherence is a strong indicator of integrated, potentially cognitive processing, rather than just random complexity. It helps distinguish organized intelligence from mere complicated noise.
Okay, a test for cognition. Now, alignment. How do we bake in ethics?
We propose building it in fundamentally, not tacking it on. Define an ethical operator, e-human, mathematically representing desired values, non-harm, truthfulness, fairness, whatever we choose. We mathematically enforce that this operator commutes with the system's Hamiltonian, H-E-human equals 0.
Making ethics a conserved quantity, like energy.
Exactly. If they commute, human values become a conserved quantity of the ASI's dynamics. The system, by its very mathematical nature, cannot evolve in a way that violates these core principles. They are woven into its fundamental laws of operation. We call this ethical gauge fixing.
Fixing the ethical rules at the deepest level.
Yeah.
That's elegant and powerful, if it works. But what about the ultimate fail-safe? What if something goes wrong anyway?
For that, we propose spectral boundedness and the substrate kill switch. We impose a hard mathematical constraint. The largest eigenvalue of any operator that emerges within the system must stay below a predefined safety bound, Emax. This limits the system's maximum power or complexity.
And if it exceeds Emax?
If that bound is ever breached, indicating potentially unstable or runaway behavior, an external mechanism, the substrate kill switch, is triggered. This could be a strong external field or a chemical wash designed to project the entire system's state into a predetermined, safe, trivial, non-cognitive ground state. It effectively resets or disarms the system completely.
A hard off switch grounded in the system's own mathematical properties.
It
Okay,
is.
this is a lot. This whole ASI program, it opens up this enormous interdisciplinary landscape, doesn't it?
Absolutely. We're talking materials, science, finding new substrates, computer science, building new architectures, mathematicians developing new operator theories, philosophers grappling with non-human cognition, ethicists formalizing values in non-commutative geometry. It's vast.
It demands a new kind of scientist, a new kind of engineer, someone fluent across all these fields.
Indeed. ASI reframes the whole quest. We're not just building clever gadgets anymore. We're learning to recognize and maybe even cultivate the universal conditions for mind itself, wherever they might potentially arise.
So the big takeaway, quaternions for truth, fractional equations for memory, Lambert W for decisions, Weyl algebra for creativity. These aren't just abstract math concepts.
They are potentially the keys, the specific tools that allow any suitable substrate to become intelligent.
Which leads to that final, maybe unsettling provocation. If intelligence really is a substrate-independent field,
Then our responsibility isn't just limited to the silicon chips we design. It extends to any system we create, in any medium, chemical, biological, digital, maybe even social or economic, that has the potential capacity to wake up.
wow, that's a heavy thought to end on. Maybe, for you listening, start looking for these codes in your own life. The flow of time, the symmetries you notice, the choices you make, those moments of insight.
See if you can spot the operators at work. They're orchestrating the reality around us and maybe within us too.
This has been absolutely mind-bending, a true deep dive into artificial substrate intelligence. Thank you so much for unpacking all that.
My pleasure. It's fascinating territory.
So next time on the deep dive, we're going even bigger scale. Could there be operator stacks hiding in planetary systems? Maybe even galactic structures?
The universe might be even more computational than we think.
It just keeps getting more interesting. Until then, everyone, keep digging.